This is the one technique I'm going to show you for integration. So with differentiation, we talk about rules like the power rule, the trig rules and stuff. With integration, we talk about techniques because it requires a little creativity and it doesn't always work. So here we go. Here's a bunch of integrals. So these are indefinite integrals. It just means I'm asking you to do a derivative backwards. And they all look hard. They look like the quotient rule or the product rule or something. But there's no such thing for integration. So all integration by substitution is the way of reversing the effects of the chain rule. So let's just go through these one by one and we're going to do them all. Cosine of x to the fourth times x cubed. You're looking for a function whose derivative is that. What I want you to notice is that the inner function is x to the fourth. The derivative of x to the fourth is 4x cubed. And there's an x cubed in there. So you're always looking at the inner function and saying, how is that related to the rest of the stuff in the integral? In that case, okay, the derivative of x to the fourth is 4x cubed. I have an x cubed in there. If I divided by 4, I could get rid of that 4. And then by the chain rule, I would have a function whose derivative is cosine of x to the fourth times x cubed. Okay, now look at the integral of sine to the fourth times cosine of x. The inner function, it's not as obvious here, is sine. The derivative of sine is cosine. So by the chain rule, if you just had some function of sine that differentiated to sine to the fourth, then the derivative of sine would pop out by the chain rule. And you have that. You have cosine. Okay? So there's a way to do it. It's called a use substitution, and that's all we're going to do today. If you look at the third one, again, it's even less obvious, but if you look at the denominator, x to the fourth plus 2x squared plus 1, the derivative of that is 4x cubed plus 4x. In the numerator, you have x cubed plus x. So that's not quite 4x cubed plus 4x, but if you divided it by 4, it would be. So you're always looking for an inner function whose derivative appears in the integrand, maybe off by a number, by a constant, like a 4 or a 2 or whatever. If you see that, then you know that this is an integration by substitution situation. If you don't see that, you can't do it. And I'm not going to show you anything that can't be done this way. So this is the way to do everything we're going to see today, is to look for an inner function and say, okay, the derivative of that is whatever it is, but we also see that in the integrand. That's the only reason this works. So this is a method for reversing the effects of the chain rule. Okay, here we go. So you look at that x to the fourth and you say, okay, the derivative of that is 4x cubed. I need that x cubed, right? And this is the one time too where you're going to use the dx. So we're going to rewrite this entire integral in terms of a new variable called u that we just make up. That's what a substitution is. You just make stuff up. But u is actually going to be a function of x. Right? So notice that. That's the only reason this works. The 4 is just a constant. So what we're going to do a little bit of algebra, basically just to say, okay, to compensate for that multiple of 4, I'm going to divide by 4. So we just make up u. The cool thing about math is you can just make stuff up and nobody gets hurt, right? It's not like chemistry where if you just make stuff up, then something explodes. You just make up a new variable called u, and you say, okay, we're going to let u equal x to the fourth. So u is a function of x, but we're just going to treat it like a variable. And this is where the dx actually does come into play. So I have to define something called a differential, which is basically the same thing as a derivative, but you'll see. So the differential of u, we call it du, and it's defined as the derivative of u with respect to x times the derivative of x. Now the derivative of x is just 1. So it doesn't, multiplying by it doesn't really do anything. But now you can finally kind of see why this Leibniz notation is the way it is, because if you just think of that thing on the right-hand side as a fraction, the dx's cancel out. So the dx is just telling you which variable you're integrating with respect to, but now we have to change that variable to u. So this entire integral, including the dx, is going to be rewritten in terms of u. So that's it. U is x to the fourth, so du is 4x cubed dx. And now look at the original integral. We have an x cubed dx. We can rewrite that all. This is just where we're at. The integral of cosine of x to the fourth times x cubed dx. We're going to let u equal x to the fourth. That way du equals 4x cubed dx. So the first part of that integral is just cosine of u now, which is easy to integrate. The next part of that integral is times x cubed dx. And we almost have that in terms of u. We have du is 4x cubed dx. We have to do the tiniest bit of algebra to make it so it's just x cubed dx. In other words, we have to solve that little equation, du equals 4x cubed dx for x cubed dx. Literally, that's just dividing both sides of the equation by 4. And there you have it. The first part of the integral is just cosine of u. The next part is 1/4 du. And now when we rewrite the entire thing, it's easy. So we've taken a complicated integral and we've made it a simple integral by making a change of variables. So when we say rewrite the entire integral, we mean the dx as well. So don't forget that part. If this seems weird, it's almost easier to do in your head in this case. In these cases, once you get the hang of it, you'll just be like, oh, there's just a 1/4 in there and it's just sine of u. But for now, bear with me. Okay, so the cosine of x to the fourth becomes cosine of u. And the x cubed dx becomes 1/4 du. That 1/4 can just come to the outside of the integral. So that just comes along for the ride, and now forget all about x. Now you just have 1/4 times the integral of cosine of u du. U is our new variable. You know that the antiderivative of cosine is just sine. So you're done. And that's the point of doing a substitution. You've turned it into something that's easy to anti-differentiate. There it is. The derivative of 1/4 sine of u plus c is 1/4 cosine of u. And now, anytime you do a substitution in math, it's like the magic trick where you have to put it back at the end. Now you have to rewrite it in terms of x. Doing a substitution is cool, and like I said, it doesn't hurt anybody, but u is still just something you made up. You, not the person you, not the variable u, now have to put it back in terms of x. You just replace it with x to the fourth. That's what u is. You defined it to be x to the fourth in the first place, so just put it back. So that's it. That's the answer. This is an indefinite integral. I'm just asking you for a function whose derivative is cosine of x to the fourth times x cubed. So the good thing about these is that you can always check them because you're so good at derivatives. So just do that derivative in your head. The derivative of 1/4 sine of x to the fourth is, okay, 1/4 cosine of x to the fourth times 4x cubed. That 4 and the 4x cubed and the 1/4 cancel each other out. So the derivative of that thing is cosine of x to the fourth times x cubed. Right? That's the thing I'm asking you to integrate in the first place. So this is just this. I don't want to call it the chain rule backwards because it's a different thing, but it's a method of reversing the effects of the chain rule. I would encourage you to do that with all of these. So like those integration formulas I told you last time, or you're like, really, the derivative of that is that? Yeah, and you know how to check that. that's how it works. It's 1/4 of outer function cosine of x to the fourth times the derivative of the inner function, which is 4x cubed, and those 4's cancel each other out. So that's all that little bit of algebra we did where we said, okay, 1/4 du equals x cubed dx. All that's doing is saying, okay, to compensate for that 4, we have to divide by 4. Again, as you get good at these, it's almost easier just to do that in your head and just know it. Oh, I'm going to need a 1/4 in this. But for now, use the u substitution, because once they get more difficult, you're probably going to have to, because this does kind of take a lot of steps. And we're going to do way more examples. This is my dog, Calvin. He's an old man and a little man, but he's a very nice guy. I thought you'd think it was funny to meet him. All right. Sine to the fourth of x times cosine of x. It's not as obvious here what the inner function is, but we know from the chain rule that sine to the fourth of x really means sine of x to the fourth. So the inner function here is sine of x. And the derivative of the inner function is literally everything else in the integral. It's cosine of x dx. So generally there's only going to be one obvious choice for what u is. It's the inner function. Once you get further into this in Calc 2 and stuff, it's not going to be as obvious. But for now, assume it'll be obvious. Whatever the inner function looks like, you better have the derivative of that thing in the integral, or else you can't do it. So the inner function is sine of x, so that's our obvious choice. U equals sine of x. Right, the derivative of that is everything else. So don't forget the dx. Du is cosine of x dx. And now look at the original integral. It's just the integral of u to the fourth du. That's it. That's easy. Right, so again, we've turned a complicated integral into a simple one by making a change of variables. So now you actually integrate, right? Because that's easy. Power rule, power goes up by 1 and you divide by that same number. The integral of u to the fourth is u to the fifth over 5 plus c. And now you can't stop there because u is just a made-up variable. So just go back to what was u again in terms of x? It was sine of x. So stick that back in. Sine to the fifth of x over 5 plus c. That's the answer. That's the antiderivative. And now again, just check it by just doing the derivative of that. You can almost do it in your head. The derivative of sine to the fifth of x over 5 is 5 times sine to the fourth of x over 5 times the derivative of sine, which is cosine, which is the original integrand, the thing I asked you to find an antiderivative for in the first place. So the c obviously just goes away, and then by the chain rule, that cosine of x hops out. So again, it's almost easier just to do a integral like this in your head rather than do the u substitution. Just say, oh, if it was just sine to the fifth, it would be, you know, sine to the fifth over 5, or 5 sine to the fourth, and then times a cosine, so you just have to divide by 5, and that's it. You're done. It's just sine to the fifth over 5. So there's one on the quiz that you're working on right now that's just sine times cosine. Just think about that as sine to the 1. It seems like it's like some kind of weird product rule, but it's not. It's just the chain rule backwards. This one, again, seems hard. But anything in math that requires you to like kind of be creative and think outside the box seems hard, because you don't like to do that in math. You just like to follow the instructions. But there aren't really any instructions here. You have to think. So look at the denominator. The denominator is an inner function. It's even less obvious here. But 1 over a thing, that thing is the inner function. So it's 1 over x to the fourth plus 2x squared plus 1. The derivative of that inner function is 4x cubed plus 4x. That's not exactly what you see in the numerator, you see x cubed plus x, but think about if you just factored 4 out of that thing, it would be. We don't have a choice. We have to let u equal x to the fourth plus 2x squared plus 1. That's nice. You don't have a choice. You can't do anything else. So do the du. Du is 4x cubed plus 4x dx. Don't forget the dx. Now, we almost have everything else in the original integral, but we need it to be x cubed plus x dx. So you solve that equation right there for x cubed plus x dx. And all that is factoring out a 4. Factor it out and then divide both sides by it. Both of the examples I've showed you with this are with a 4. 4 isn't special. That's just a coincidence. It can be 2 or 3 or any other number. So x cubed plus x dx is 1/4 du. And then it's going to be helpful to you to think about the original integral as looking like this. Convince yourself that that's the same thing. I can take that x cubed plus x and bring it outside of that fraction, because now you can really see that, okay, that's just 1/u times 1/4 du. So it's always some function of u times some number times du. Sometimes that number is just 1, like it was in the last example, and you don't need to do that little 1/4 step. So you just have to deal with it on a case-by-case basis. So now literally everything, including the dx, can be rewritten. 1/u times 1/4 the u. Bring that 1/4 to the outside. Right, constants come along for the ride. And now, again, note what we've done. We've turned a very gnarly, complicated looking integral into a very simple one. So now all you need is an antiderivative for 1/u. Think about it. You know what that is. It's the natural log function. 1/4 natural log of the absolute value, that's actually important here. You need that, of u plus some constant. Hard part's over. Just stick whatever u was back in. So u was x to the fourth plus 2x squared plus 1. That's the answer. 1/4 natural log of x to the fourth plus 2x squared plus 1. And again, I insist that you check this by differentiating, because once you do that enough, you'll see why this works, and you'll kind of figure out how to skip the whole process. So the derivative of 1/4 natural log of absolute value of x to the fourth plus 2x squared plus 1 plus c is, okay, 1/4 times 1/x to the fourth plus 2x squared plus 1 times the derivative of that, which is 4x cubed plus 4x. What happens to that 4? It gets canceled out by the 1/4. That's that whole middle process. That's all you're doing, is saying, okay, whatever constant hops out of there by the chain rule, I just need to cancel it out. Right, so do that. Again, I insist that you do that. If you don't, you won't really understand what is happening here. You are reversing the effects of the chain rule by doing all these little middle steps. So this is what I mean when I say integrating is harder than differentiating. We don't call them rules, we call them techniques, because it doesn't always work, and you need to do a little work to even get them. Okay, so that's the important part. One more. We don't have a function whose derivative is tangent. We don't have an antiderivative for tangent. But we will. This doesn't look like a candidate for doing a u substitution, but here's how we do it. So you all remember from trig class that the definition of tangent is sine over cosine. So just rewrite it as a fraction like that. This is actually exactly like the last one. The derivative of the denominator is the numerator. except it's off by a negative sign, but a negative sign is just like a constant. You just throw another one in there and it cancels it out. So we have a little bit of ambiguity. The derivative of sine is cosine, but you can't pick sine to be your u because sine is not an inner function, right? Then you would have like a 1 over du thing. You have to pick the inner function to be your u. And the only function that can truly qualify as inner here is cosine. So think about this again as sine times 1 over cosine. Cosine is your only choice for the u substitution. It wouldn't work the other way, right? So again, it's exactly like the last one. You let u equal the denominator, and then you do the du. And that's the only reason it works. Yeah, it's negative sign, not sine, but that little algebra move is going to just let us say, okay, well, there's just a negative in it. So u has to be cosine of x. Du is just the derivative of cosine, which you know is negative sine. So du is negative sine of x dx. You solve that equation for all the other stuff you need, which is sine of x dx. And all that means is just multiplying both sides by -1 or dividing both sides by -1 or however you think about that thing I just did. Right, and anytime you have one of these that's a fraction like that, it's helpful to rewrite it like this. It's 1 over cosine times sine of x dx. So now you just have, okay, that first thing is 1 over u, easy. That next thing you know is just negative du. So it's 1 over u times negative du. So it is literally times. So that dx that I initially said is just, it means with respect to ignore it. No, it actually means something. It means times dx. And when you only have one variable, dx is just 1. But now that we're changing things, it becomes this other thing that tells you, okay, now it's with respect to u. Much simpler, 1 over u times negative du. That negative is just a constant, which comes out front. Is just negative 1 over u du. So we turn that whole thing into just a antiderivative for 1 over u, which we all know is just natural log of the absolute value of u. Hard part's over. Just stick back in whatever u was in the first place. U was just cosine of x. Don't forget the absolute values because, again, they are important when we're going this way. It's negative natural log of absolute value of cosine of x plus c. So you get some unexpected things here, you're noticing. You wouldn't think that that function, the derivative of that function is tangent, but it is. And in another move, I'm gonna say just check it. Do the derivative of that thing. All the weird stuff goes away, and all you're left with is tangent. So if you stopped here, you wouldn't be wrong, but this is not what you'll see. So when you look up tangent in an integral table and in Calc 2, when you maybe have to memorize this stuff, you will not see negative natural log of cosine. You will see it as natural log of secant, and I'll briefly explain why. We had a power rule for logarithms where we said, okay, the log of something to a power equals that power times the log of that something. So logs make powers hop out front as constant multipliers. You have seen that, you know that, you knew that at one point in your life. So if we do that power rule for logs backwards, we can bring that -1, that's a constant multiplier, inside of the logarithm as a power of -1. Just bear with me. So that's the same thing as natural log of absolute value of cosine of x to the -1. Now don't confuse that with arc cosine. This is literally cosine to a power. So that's the same as 1 over cosine. So that's natural log of 1 over cosine. What's another word for 1 over cosine? Secant. That is the integral for tangent of x that you will see forever in any integral table you ever look at or you Google because you forgot it or whatever. Google integral of tangent, you're going to see natural log of absolute value of secant. So again, the thing we got in the first place wasn't wrong. This is just rewritten in a way that I guess somebody at some point said was simpler. And so that's just, it's got to be one way or the other way. So this is just the way it is. Always check by differentiating. You can do this step in your head. Think about the derivative of natural log of secant. It's 1 over secant times the derivative of secant, which is secant times tangent. Oh, those secants cancel out, don't they? So what are you left over with? Just tangent, right? So that's what that little substitution rule wizardry does, is it tells you how to get stuff to cancel out so that everything goes away except the original integrand, which in this case is tangent, right? So you can do that with every trig function. You can't do that with more complicated functions. You need Calc 2 moves. So hopefully I'll see you in Calc 2.